The last thing we'll finish section 3.3 with is a discussion on higher order derivatives. Just as we obtained the velocity function by differentiating the position function, we can obtain an acceleration function by differentiating the velocity function. Another way of looking at this is we can obtain the acceleration by twice differentiating the position function. So as we've seen before, if s of t represents position, then the velocity function is the derivative of position, so velocity is equal to s prime of t. Now, the rate of change of velocity, which should be given by v prime of t, that's what we call acceleration. So acceleration is the derivative of velocity, which in turn we can think of as being the second derivative of position. And notationally we'll call that s double prime of t. That represents the second derivative of s with respect to t. So acceleration is the second derivative of position, and there's really nothing from stopping us. We can continue actually to take more derivatives, and this is kind of notationally what that would end up looking like. We've already seen our notation for the first derivative previously. The notations we would see for the second derivative would look like this. It's either f double prime. If we look at the Leibniz notation, it's going to be d squared y dx squared. Or we could have y double prime. Or if you're thinking of it as kind of applying an operation, the derivative as an operation, we'd have d squared dx squared of a function f of x. Or an operator notation, d squared y. Similarly, the third derivative would be f triple prime. Or we could call it d cubed y dx cubed. Or y cubed similarly. Once we move, though, beyond the third derivative, we'll start to put the number of the derivative in like a parenthesis. So like, for example, if I wrote this, okay, please be very careful. This does not mean the fifth power of x. The fifth power of x would be this, with a power of 5. When we put the 5 in a parenthesis, this actually indicates the fifth derivative of x with respect to, the fifth derivative of f with respect to x. The Leibniz notation stays consistent. The nth derivative would be dny, dxn, or yn, etc. In example 9, they ask us to compute the first four derivatives for the function f of x equals 5 cosine of x. So let's go ahead and do that. So starting with f, we have f of x, which is 5 cosine of x. We know from prior how to calculate f prime. F prime of x, the derivative of cosine is going to be negative sine. So we get negative 5 sine of x. To this function, we can take its derivative, which gives us the second derivative. The derivative of sine is cosine, so it's going to be negative 5 times cosine of x. If we differentiate the second derivative, then that's going to give us the third derivative. This is going to be negative 5 times the derivative of cosine is negative sine of x. So this is positive 5 sine x. And then if we go one more time, the fourth derivative, which we would write like this, f parenthesis 4 of x, the derivative of 5 sine of x is equal to 5 cosine of x. So there's our first four derivatives for the sine 5 cosine of x. And if you're kind of paying attention or looking closely, notice that it actually turns out that for the cosine function, it kind of has the unique functional relationship that its fourth derivative is actually equal to the original function itself. And in general, this is true of the derivatives for both sine of x and cosine of x. They are periodic and they actually cycle with period 4. So if you take the cosine function and you differentiate it 4 times, you actually return and get back the original cosine function. And the same is true of the function sine of x as well. Let's take a look at one last example. This is example 10. Suppose we have the position function for an object dropped from a height of 2 meters on the moon. This given by s of t equals negative 0.81 t squared plus 2, where S of t is the height in meters and t is the time in seconds. Find the velocity and acceleration functions. Okay. So let's do that first. So if we want the velocity function, we know that velocity is the derivative of position. So this should be s prime of t. If we differentiate this function, we have to bring the 2 down in front. Negative 0.81 times 2 would give us negative 1.62t. The derivative of the constant 2 would be 0. So this would give us our velocity function. If we wanted to find the acceleration function, let's call it a of t. A of t is the derivative of the velocity, which is equivalent to taking the second derivative of position. If we take the derivative of negative 1.62t, we simply get negative 1.62. And unsurprisingly, this is actually a constant, and it would actually be the gravity on the moon. So gravity on the moon, it turns out, is given by negative 1.62 meters per second squared. The question asks, as a follow-up, what is the ratio of gravity on the Earth to gravity on the moon? Okay. So we want the ratio of g of E to g of the moon. If you're curious as to why there's the negative sign, any body that's, or any thing that has mass that's on these planets will always act towards the center. So it'll always kind of act in a downwards vertical fashion. G of E is negative 9.8 meters per second squared. Gravity on the moon, we said, was negative 1.62 meters per second squared. The units cancel, so this is going to be a dimensionless ratio. And if we look at that ratio, we end up getting approximately, it's going to be a little bit, just a tad bit more than 6. So it's approximately a factor of 6. Okay. So gravity on the Earth is 6 times that as what it is on the moon.